Let's break a candy cane. I pulled on the candy cane and it broke suddenly and without warning. There was no plastic deformation of the candy cane before fracture, and therefore the break was clean and pretty much straight across. Now, let's break a ginger candy. Notice that the ginger candy deforms a lot before it fractures. You can pretty much predict when it will finally give way. The candy cane and the ginger candy are great illustrations of the two modes of fracture: brittle fracture and ductile fracture. I bet you can guess which candy represents which type of fracture. Just by viewing these two videos, you have visually experienced the characteristics of these two modes of fracture. But let's list them anyway. Brittle fracture is characterized by little or no plastic deformation, low energy absorption by the material. The fracture is sudden and can be unexpected. Ductile fracture is characterized by significant plastic deformation, large energy absorption by the material, and predictable fracture. This is why we call ductile fracture stable and brittle fracture unstable. Brittle fracture has been known to be catastrophic. What you see are two different tensile test specimens before and after being tested. Remember, a tensile test is simply pulling on a specimen until it breaks and measuring the force and elongation. Can you tell which material is ductile and which material is brittle? The one on the right is ductile. You can tell because it experiences plastic deformation before it fractures. Tensile toughness is defined as the amount of energy absorbed by the material before fracture. You can determine the tensile toughness by calculating the area under the stress-strain curve. You can see that a brittle material absorbs far less energy prior to fracture than does a ductile material. Let's categorize the items that you see on the screen as either something that would experience brittle fracture or ductile fracture. So, what about the glass? Brittle fracture. And the plate? Brittle fracture. Now what about the copper wire? Ductile fracture. And the steel? Ductile. Okay, now for something harder. What about the pen? I'll give you a hint. This one is a trick. Have you ever taken the top off of one of these pens and bent back the tab? Did it break or bend? It bends. Okay, now did you ever try to bend the body of a pen? Did it bend or did it break? It broke. It might be hard to break, but it didn't bend and stay that way. So the pen top, which is one type of plastic, is ductile, and the body, which is another type of plastic, is brittle. Okay, last item. What about the cast iron skillet? Cast iron, because of its large carbon content, is actually a brittle material. One major downside of brittle materials is their inability to handle flaws. That means small cracks, imperfections, or manufacturing flaws. Would it surprise you that the theoretical strength of glass is greater than the theoretical strength of aluminum? But because no material is perfect and all materials have flaws, glass doesn't have the tensile strength of 17,000 megapascals. It only has a strength of 7. That's quite a reduction. Now, on the other hand, ductile materials are much more forgiving of flaws. Aluminum's theoretical strength is 12,000 megapascals, but its actual strength only decreases to 90. So why is this true? It all has to do with stress concentrations and crack propagations. We'll talk about stress concentrations next. But in brittle materials, once a crack starts propagating, there's no stopping it. However, ductile materials absorb energy. That's why it's so hard for cracks to propagate through them. So what is stress concentration? Let's say that I have a steel bar. It's fixed at one end, and I am pulling it at the other end. I think that this bar will not fail, because I did all the calculations and the stress within the beam is below the yield stress, which is 0.28 gigapascals. See how most of the bar is green? And the stress key says that the green area is below this stress. But what I didn't realize was that there was a small imperfection in the beam, a notch, and anywhere there is an imperfection or a change in area, there is an amplified stress or stress concentration. Look at how the color changes in this area. The stress increases to a value above the yield stress. So every time there is a flaw, small crack, or manufacturing imperfection in a material, stress will be amplified. And that is why no material will reach its theoretical strength. It's just that brittle materials are more adversely affected by these flaws than ductile materials are.